Yes, I'm sure. Ha. Welcome to class. So when we're taking related rates in calculus, we are always taking the derivative with respect to time. So the derivative of some formula with respect to time. Okay, and chances are we're going to be using implicit differentiation a whole bunch when there are a lot of different implicit differentiation when we're doing these types of problems. Okay, so every time we take a derivative of something, we're going to have a d blank dt. So radius will be dr dt. What else we got in there? Height would be dh dt. Right? Many of these things will be unfolded to us as we go. So we're just going to first start by taking the derivative of a bunch of formulas. Okay, practicing some implicit differentiation. Okay, so I'm going to pause the video and do all this work together. So you should pause it and do it together and then come back and see if you got it right. Okay, there we go. So hopefully you see that every time you take a derivative, you get a rate. So the derivative of an area is dA dt. We have a rate. Okay, and we have dr dt when we take the derivative of r. Every one of these, every variable you have, has a rate associated with it. Okay, especially the trig one. The trig one has to have a rate about your angle, and it has to have a rate about your variable, your side length for your triangle. Okay, and then there's the volume of the cone, which we'll try and simplify every time we do a volume of a cone problem. Okay, so let's look and see how this works with an actual problem. So here we have air leaking out of a balloon in the shape of a sphere. Okay, so this should tell you right now that we have a volume. Okay, if air is leaking out of a balloon, we're looking at a volume for a sphere. Okay, volume. The instant the radius is 4, oh, this is the rate, this is important, underline the rate, at a rate of 230 pi cubic centimeters per minute. Okay, so this is our rate, right? The rate of our volume. So this is our dV dt, the rate that the volume is changing. Okay, air is leaking out. Air represents volume. We know the radius is 4 eventually, so we'll plug that in. And we want to find what is the rate of change of the radius. Ooh, I think it's okay. Looks like I got. So we're looking for dr dt. Okay, so the rate of change of the radius, the derivative of the radius with respect to time. So let's start with our formula for volume of a sphere. Volume equals 4/3 pi r cubed.
This is number 4, right?
Okay, now on your AP test, you will be given that formula. Chances are you don't have to memorize them, but learning them wouldn't be a bad idea. All your formulas. Okay, so we start with a formula. The volume of a sphere is 4/3 pi r cubed. Okay, and now we're going to take the derivative with respect to time like we did up above. So now that we have our derivative, we can replace the things that we know. Okay, dV dt, the derivative of the volume, the rate the volume is changing. Okay, the rate the volume is changing is 230 pi cubic centimeters per something per minute. Okay, so 230 is our rate that the volume is changing. We still have a 4 and a pi. Now, what did it say our radius was?
4.
Our radius is 4, so that's 4 squared, and we're going to solve this for dr dt. That is the thing that we do not know, the rate at which the radius is changing. So basically, this is a division problem once you take the derivative and you plug in everything that you know. So we have 230 pi. 4 squared, well, that's 16. 16 times 4 is 64. And if you need a calculator, by all means, use a calculator to multiply these things and divide them. Okay, so then to solve for the rate, we're just going to divide both sides by 64 pi. Okay, it becomes a nice algebra problem. So the rate of this sphere is changing at whatever 230 divided by 64 is. So let me find a calculator, and that comes out to be 3.594. And the units were, let's see, what were the units? Centimeters per minute, right? So this is a radius. A radius is a linear distance, so it's just changing at centimeters per minute. Okay, it probably would have been okay also if you wrote 230 over 64 centimeters per minute, right? If this is an FRQ, you could leave it as a fraction. You do not have to decimalize that on an FRQ, right? On the multiple choice section, maybe they wrote it as a decimal and you would have to match. But as far as FRQs go, leaving it as a fraction is a safe stopping point. Okay, let's look at some more examples of rate problems in calculus. Okay, a stone is dropped into a calm body of water and causing ripples to form circles. Okay, so think everything you know about circles, right? We have circumference of a circle. We have radius, diameters, right? Circles have diameters and circles have areas. The radius of the outer ripple is increasing at a rate of 1 foot per second. Okay, so radius, right? That is the rate of our radius. So that's dr dt. The radius of the outer ripple is increasing at a rate of 1 foot per second. That is dr dt. The rate your radius is changing. When the radius is 4, at what rate is the area of the water changing? So this is an area of a circle problem. Area equals pi r squared. Okay? So that's where we start with a formula, the area for a circle. And now let's take the derivative with respect to time. So the derivative of area is dA over dt, right? Derivative of area with respect to time. We're going to differentiate, or rather derive, pi r squared, which becomes 2 pi r times dr dt. Every variable will get a rate. Okay? So now it's just a matter of plugging and chugging. We know that the radius is 4 feet. When the radius is 4 feet, the radius is increasing at 1 foot per second. 1 foot per second. So let's see. If I multiply these together, I get what? 8 pi? Yep. So the area is changing with respect to time at a rate of 8 pi. And let's see. We have feet per second. So square feet per second, because area is a squared unit. So the units of rates for area are square feet per second. Okay? And that's a rate problem. Ain't nothing to it. All right. Let's see what else we got here. Water is leaking out of a cylindrical tank. So that's the tank in the shape of a cylinder. Okay, so here we have a cylinder at a rate of 3 cubic feet per second. So probably volume of a cylinder. Okay, so volume for a cylinder, according to our geometry, was the area of our base, which is pi r squared, times the height. Pi r squared h is how we calculate the volume of your cylinder. Hopefully, that will be given to you in the equation on the problem. If the radius of the tank is 4 feet, at what rate is the depth? So remember, depth is height, right? Depth and height mean the same thing. The height of the water and the depth of the water mean the same thing. Okay? If your water is 4 feet deep, then the height of the water from the bottom is 4 feet. At what rate is the depth of the water changing? So dh dt, the depth, the height, the change in the height, at any instant during the leak. Any instant. Okay, so not at any specific time, but all the time. So let's see. Okay, so what is not changing here?
Radius.
The radius, right? This thing is not getting any skinnier. The cylinder it's not like a cone. It doesn't have a point. So the radius is always going to be 4. And I know what 4 squared is. That's 16. So the volume of this particular cylinder is always going to be 16 pi times the height. 16 pi times the height. So now let's derive this according to time.
You cannot derive it before you plug in the radius?
So we have dv dt. If you want to, yes, you can take the derivative. Oh, no. No. Plug in radius first. Okay, because the radius isn't changing. Right, because if it was, now we have a product rule, r squared times h, and it's going to get a little messy. So if we can simplify it by plugging in the constants, let's do that. Okay, so dv dt equals 16 pi, because that's the coefficient of height, times dh dt, the change in our height. The change in our height is that one. Okay, so we're told that it is leaking out at 3 cubic feet per second. Okay, so if it's leaking out, the volume has to be decreasing, so this is a negative rate. Right, so if the water is leaking out, then we have less volume and the height is going down. Right, so the height, it will be negative, it will be losing height, equals 16 pi dh dt. So with one little division here, I will get the height is changing at a rate of -3 over 16 pi, and my units are cubic feet per second. So because height is linear, right, it's just changing at a rate of feet per second. So -3 over 16 pi, whatever that happens to be, right? That's a number, that's a decimal. I don't have a calculator. This is a safe answer on your FRQ. You do not have to simplify that on the AP Calculus exam. Ooh, this is getting good. Okay, how about this next one? A 20-foot ladder is leaning against a vertical wall. It's good that the wall is vertical. Okay, let's draw this situation. Shall we? I think we shall. A vertical wall. Okay, we're going to also assume that the ground on which the wall is situated is also perpendicular to the vertical wall. Okay? Just for fun, right? Because if it wasn't, then we'd be looking at the law of sines and cosines, which is going to be tedious. So we're going to assume that that's a 90-degree angle. Okay, we have a 20-foot ladder, so the ladder is 20 feet. Is the length of the ladder ever going to change? No, it's not going to change at all. Okay, the base of the ladder, so that's down here, is being pulled away from the wall, so it's moving in this direction at a rate of 1/2 of a foot per second. Okay, so it's moving away from the wall, which means the top of the ladder is going in what direction?
Down.
Right, the ladder is coming this way. It's moving in a negative direction. Okay, it's important to know that moving down in a calculus problem is a negative direction. Okay, so how fast is the top of the ladder moving down the wall the instant the ladder is 10 feet above the ground? Okay, so this is a Pythagorean theorem problem because it's a right triangle. So usually if we're looking at the horizontal and the vertical axis, the horizontal is your x-axis. Yes, we'll call the horizontal length x, and we'll call the vertical length y. Okay, so the vertical is our y, the horizontal is our x. So according to Pythagoras, x squared plus y squared equals 20 squared. Okay, that's what the Pythagorean theorem would state when we have some numbers. So let's take the derivative of that. Right, that's our formula for every right triangle in this case. Okay, so the derivative of x squared is 2x times the rate, right? Every variable gets a rate. So this is dx dt. Dx dt. Every variable that you derive gets a rate. Plus, how about 2y? I mean y squared. 2y times dy dt equals, what's the derivative of a constant? 0. The derivative of our constant is 0. Okay, so it's constant, right? There's no change in our ladder length of our ladder. One of those two things. Okay, so let's see. What do we know? What don't we know? How about that? Do we know x? No. Do we know y?
Yeah.
Yes, when y is 10. So if we're going to draw this picture, right, we want to know what is the rate when this is 10 and this is 20, and we don't know what this is, right? We don't know the length, but we know the rate. We do know the rate. So we have to use Pythagoras, or in this case, special right triangles, if you recognize that the hypotenuse is twice as long as one of the legs, that means this is a special right triangle. But let's say you didn't realize that. 10 squared plus x squared equals 20 squared. Okay, says Pythagoras. So x squared equals 400 minus 100, because that's 20 squared minus 10 squared. So x is the square root of 300, which I'm going to leave just like that. Okay, so now I know what x is, I know what y is, and I know my rates. Yes, I know my rate here. Okay, so let's do our plug and chug. We have 2 times the square root of 300, okay, which was the length of my x, times the rate of x, which is 1/2 feet per second, plus 2 times my y value was 10 times dy dt. That's what I'm looking for, right? The how fast is the top of the ladder moving down the wall. That's my y change, equals 0, right? Equals 0, the derivative of 400. So we're going to take all of this and subtract it to the other side, right? This is just an algebra problem now. So I have 20 dy dt's, that's 2 times 10, equals negative root of 300. Okay, because 2 and the 1/2, 2 times 1/2, that's just 1. Equals negative 300, root 300. Sorry, this is dy dt down here, not dy dy. So now when I divide both sides by 20, I get a rate of negative root 300 divided by 20. And I believe my units are feet per second, okay, which is some number, right? That's a decimal. Root 300 is less than root 400, so that's less than 1, which is fantastic. That is a great looking rate. So our ladder is sliding down the wall. It's a good thing it's negative, right? Because our y value is decreasing, so we're expecting to have a negative rate anyway, which is super. Dy dt is that. Good job using Pythagoras. Okay, how fast is the angle of elevation of the ladder changing at that same instant? Okay, angle of elevation, what does that mean? So let's go back to our geometry from years and years and years ago. If I have a right triangle, okay, and this is the base of my ladder, this becomes my angle of elevation. Okay, so this is the angle that I am being asked for. How fast is that changing? So let's go ahead and do this math here. So what type of relationship is going to happen with this angle? Probably a trig relationship, right? If we're talking about angles, we're talking about trigs. We know that the hypotenuse is always 20, right? And we know this side was 10, right? When at that instant, right? When y was 10. So we can set up is this a sine? Looks like the sine of theta equals, well, we know that's 10, so maybe 10 wouldn't be the best to put in there. On a y over 20, right? The sine is the opposite over the hypotenuse. So if I want to make an equation, then I have something like that. So sine of theta is y over 20. Okay, which I'm going to write as a product, 1 over 20 times y, because now I want to take the derivative, right? I want to figure out how fast is my angle changing. My angle is changing, how fast? So I need to take the derivative and figure out what that angle is. So sine theta, what's the derivative of sine theta? Cosine theta times, right, we need a rate. So what is our rate? D theta dt, right? Every variable needs a rate, and theta is a variable. Equals 1 over 20 times the derivative of y, which is dy dt. Dy dt. Okay, which, by the way, we just found over here, right? This is my dy dt. So I can take this answer, and I'm going to plug it in right there here in a second. In fact, let's do it right now. 1 over 20 times negative root 300 over 20 also, right? So that's the rate at which my y is changing, dy dt. I calculated that a second ago. So that's negative root 300 over 400. Over 400. Equals cosine of theta times d theta dt. Okay, usually these trig ones are kind of involved. So, cosine of theta. I really wish we knew what that angle was so we could figure out what this number is. Any way we can figure out what this angle is?
Nope.
Sure there is. We know that the sine of the angle is 10 over 20, right, at this instant. So we know our y value is 10. So the sine of the angle is 10 over 20. So the angle is where the inverse sine, so the angle where the sine is 1/2. Okay? The angle where the sine is 1/2. If I look at my unit circle, where my y value is 1/2, that comes out to be 30 degrees, or pi over 6 if you are a radian fan. So the cosine of 30 degrees, what is the cosine of 30 degrees? If the sine is 1/2, that means the cosine is root 3 over 2. Yes? Do we all follow? If the sine at 30 is 1/2, that means the cosine has to be root 3 over 2. Okay, so now I have this. I replaced cosine theta with cosine 30, because that was the measure of that angle. And that equals this amazing fraction. So now when I multiply by my reciprocal, right, this is a lot of stuff. I will not tell you the lies. This is a lot of stuff. Multiply by 2 over root 3. Okay, because we multiply by the reciprocal whenever we're trying to get rid of a fraction. Okay, so d theta dt, the rate of our angle is changing. Okay, these can cancel and give me a 200 on the bottom. What is root 300 divided by root 3? Okay, those are both roots. So that's the same as root of 300 over 3. Oh, that's 100, huh? What's the square root of 100? 10. Amazing. And then 10 divided by 200 is negative 1 over 20. And I think these looks like they're going to be an angle. So let's talk about degrees per minute. So the angular elevation is not changing very much, but it is getting smaller, right? So we would expect a negative rate for that. Wow. That turned out to be more than I was ready for. But there's a lot. Okay, so yes, so trig ones, whenever we're finding angles, that's going to be a lot. But once again, this is how we find rates in calculus.